Hey Scholarship Kiddies, and welcome to lesson 5 on back titrations. So we're just going to jump straight into it. So why do we do a back titration first of all? Back titrations are nice and fast. They avoid competing reactions happening, and they show a really nice endpoint, which makes the color changes really nice so that we can see the endpoint better. So an example of a titration that needs to be a back titration is if you were trying to work out the alcohol content in a solution with acidified dichromate. It doesn't give clear results because the alcohol can form both the aldehyde and the carboxylic acid, so we have to do a different method instead. So that's just an example of how it can be useful. So what is a back titration? So it's quite hard to explain through a bunch of words, but I'm going to do my best to explain it. So basically you could have a sample here, and I know my terrible drawings, it could be a solid or an aqueous, but I'll do a solid for instance. And what I'll do is, say I don't know the mass of this, so this is an unknown mass of a substance, then I would add a measured excess with a known concentration of something that I know will react with that substance. So I have to know what it is, I just can't know its mass. So I add in here a known amount, so I'd have known concentration and a known volume that I add in there. And that would be the total amount of substance that goes in. Now, I'd give that a bit of a mix and allow them to completely react. Now, because I've added this in excess, this liquid in excess, that means that all of X will react. And so then I'll be left with the products of that reactant, but there'll also be a bunch of that reagent that I've added in excess. So there'll be excess left over that hasn't reacted. So what we then have to do is, using this flask with the products and what's left over, the excess amount, we do a titration, okay, with your burette, and we do a titration where we add something that we know will react with that excess substance. And so if we do a titration, we always have to know the concentration of that substance, and the burette or the end point will tell us the volume. And so we can then work out the number of moles of the substance we add from the burette that was required to react with the excess substance, okay? And if we know how much is reacted with the excess, and we know the total amount of excess that was added at the beginning, then we can take the total, subtract off the amount from the excess, and that'll tell us the number of moles of X. And if we know the number of moles of X, then we can times it to the molar mass to get the mass of X. And this is just one type of example. So I'm actually going to do an example so hopefully it makes sense. So X this time is going to be sodium carbonate. So in my flask here, I've got X amount of sodium carbonate. Okay, so Na2CO3. And what I'm going to do is I'm going to add a known amount of HCl into this flask. So I'm going to add 50 mils of 0.1 HCl, and that's the total amount of HCl that I'm going to add, and that's an excess, okay? So there's far more HCl added than can react with the sodium carbonate. Now, when that happens, the sodium carbonate will end up forming a salt and water and CO2. So we know that reaction, we can do it here. So Na2CO3 plus 2HCl goes to NaCl, and there'll be two of those, plus CO2 plus H2O, okay, and you're going to need, that's it there. Okay, so that's the equation, and so you produce that neutral salt and water, and carbon dioxide will escape. So all of that reacts, you actually have none left, and so what we actually have in here is H2O and NaCl, but we have a whole bunch of excess HCl that hasn't reacted. Okay, so a whole bunch of HCl that hasn't reacted. So what we then do is we do a titration where we use a known amount of sodium hydroxide, a concentration, and from the titration we'll get the volume. And so that's going to react, and it's going to react with this excess HCl. And if it reacts with that excess HCl to reach the end point, and because we know the C and we get the V from the burette, we can work out the number of moles of NaOH that are added to react with that excess HCl. And we know that HCl and sodium hydroxide, they react in a 1-to-1 ratio. So whatever the number of moles of NaOH is, it's going to be the same for the number of moles of HCl that's left over, the excess HCl. And so that's just what we do. So we work out the number of moles, C times V from there, and we know that's going to equal the same number of moles of the HCl in excess that was left over in the flask here. And if we know the number of moles of HCl from the beginning, because we had a concentration and a volume of the total amount of HCl added. So if we've got total HCl, and we know the number of moles of total HCl, and we know the number of moles of excess HCl that was left over afterwards, then we can subtract that the number of moles of HCl excess, and that'll give us our number of moles of HCl that reacted with the sodium carbonate. And then we can use this balanced equation showing us it's a 2-to-1 to work out the number of moles of sodium carbonate, and therefore once we've got the number of moles we can times it by the molar mass to get the mass. So I've done this all neatly on the next slide, but that's a rundown of what's happening. Okay, so this is just showing exactly what we did there. So there's a part of a tablet, unknown mass, and then they've added HCl, okay, and then they've done a titration with sodium hydroxide. So anyway, let's just go through. So this first step here, the number of moles of HCl, that's your total number of moles of HCl that was added in the beginning. So 50 mils in 0.1, and you've got 5 times 10 to the negative 3 moles. The next step is to work out the number of moles of the sodium hydroxide that we add, okay, and so C times V, that's the number of moles there. Now, we know that HCl and sodium hydroxide react in a 1-to-1, so this number of moles also equals the number of moles of the HCl in excess. Okay, so that's going to tell us the number of moles of HCl that was in excess in this reaction that didn't react with our sodium carbonate. And so we do that, 5 minus that, and that tells us that's how many moles of HCl was left over after the reaction. Oh, sorry, this number of moles here tells us the number of moles that reacted with our sodium carbonate. Okay, because that's the number of moles that reacted, that was left over. So if this is the number of moles of sodium carbonate, or the HCl that reacted with the sodium carbonate, I should say, we can use the number of moles of the HCl to then work out the number of moles of the sodium carbonate, and we can see that it's a 2-to-1 ratio. So whatever our number of moles here of HCl is, we can half it to work out the number of moles of our sodium carbonate. So if we half that value, we get 1.34 times 10 to the negative 3 moles. And then to work out the mass, we times it by the molar mass there, and we get 0.142 grams, and that's written to 3 significant figures. So I'm just going to run through it one more time to make sure we've understood the process. So we added a total amount in excess of HCl to the flask, and all of the X amount of sodium carbonate reacted, and some of this HCl was left over. Now the leftover HCl we then titrated with sodium hydroxide. We knew its concentration and we got its volume from the burette, okay, and so that was the number of moles of sodium hydroxide added, and as HCl and sodium hydroxide reacted in a 1-to-1, that told us the amount of HCl that was left over in excess after the reaction with sodium carbonate. So if that's the case, if this is the number of moles of HCl left over after the reaction with sodium carbonate, we can subtract off from the total amount added how much HCl must have reacted with the sodium carbonate. And so this is the number of moles of HCl that reacted with the sodium carbonate initially. And if we know that number of moles, we use our balanced equation, and we can see it's a 1-to-2 ratio, so we have to half the number of moles of HCl to get the number of moles of sodium carbonate. And once we know that, we can times it by the molar mass to get the mass of our sodium carbonate. Hopefully that makes sense. Okay, so back titration example 2. So this one is saying that X grams of cyclohexene was added to 50 mils of 0.2 iodine. Okay, so the first thing to note is that iodine can react with cyclohexene in this reaction here goes from unsaturated to saturated. So remember, whatever we're adding, which in this case is iodine, has to be added in excess for this whole process to work. So more iodine is being added to the flask than what the cyclohexene can react with. So all of the cyclohexene will get converted to this, and then we will have leftover I2. Okay, now the leftover I2 is then 10 mils of the sample, so 10 mils out of the 50 mils, 10 mils of the sample is titrated with sodium thiosulfate, which we've seen a lot of now in the redox lessons. So iodine reacts really well with sodium thiosulfate, and a recap as to what the indicator is here is it's a starch indicator, because starch goes black with iodine and it goes colorless when it forms I-. So what we're doing here is initially the cyclohexene has reacted with iodine and formed this, and then there's leftover iodine in our flask. So we take a sample of that leftover iodine and we react it with sodium thiosulfate. Sometimes we have to take a sample because the volume is simply too large to be able to do one burette titration. So that means that the titer volume out of the burette would be too large, and if you have to refill your burette for one titration, you introduce or double the absolute uncertainty, or the percentage error I should really say, and so therefore it's no good. So we have to just take a sample and then amplify it afterwards. So we take a sample which we know has got heaps of leftover I2, and we react it with thiosulfate. So I2 forms I- and thiosulfate forms S4O6 2-, and here's the balanced equation, and you can see here that it's a 1-to-2 equation. So the first thing that we can do is work out the total amount of I2 in that 50 ml sample to begin with, C times V, and we see it's 0.01 mol. So that's timesing these two together from the beginning. The next thing we can do is we can work out the number of moles of thiosulfate that react with 10 mils of the sample. So don't forget this 10 mil things, it often trips up kids. So C times V, and you'll get this many moles of sodium thiosulfate that reacted. Okay, so the next thing that we have to do is look at our relationship between sodium thiosulfate and iodine, and it's a 1-to-2 relationship. And because we've got the number of moles of iodine, we have to half that amount to get the number of moles of I2. So the number of moles of I2 is 6.3 times 10 to the negative 4 moles, and that's in the 10 mil sample. So what we need to do now is, what would that have been if it was the full-on 50 mil sample? And so 10 mils is 5 times smaller than 50 mils. So if we times it by 5, that'll give us the number of moles that would have of iodine that reacted in the whole sample if we had been able to test the whole sample. So that's the I2 that would have been able to react with sodium thiosulfate in the whole sample. So if we have that, and we have our initial number of moles from the beginning, which was this one here, then we can subtract the two, and that'll tell us how many numbers of moles of I2 must have reacted with our cyclohexene. And so we do that, and we can work out that 6.85 times 10 to the negative 3 moles of I2 must have reacted with cyclohexene. And you can actually see from this equation, it's a 1-to-1 ratio here. So this is actually the same number of moles as cyclohexene. And so, therefore, to work out the mass of cyclohexene that was added, we times it to the molar mass, and we get 0.563 grams. So hopefully that makes sense. The whole thing of a back titration is you have to work backwards from the second step to then come up with the answer. Please let me know if you have any questions. I'll be coming back with a part B soon.